I can't think of a better way to start a retro hacking day than with Echo and the Bunnyman. Saw them at the Bismarck in '84. The Flesh Tones opened for them. And of course, YouTube will make me take this down if we listen to any more of it, I guess. Or so I've heard, right? Anyway, vinyl, mid-'80s, perfect for hacking on the retro board. So last week I did what all software types do, and that is I broke something that works. Now, with good reason here, okay? So follow me along here. We had a read routine that worked. The write routine was stubbed in with a little error return flag, right? So why did I mess up the read routine? Okay, so what we have here is the same debug we've been looking at before. I'm leaving this in there so you can tinker with it if you want. Eventually, I'll probably throw this away. It's so much noise. I don't know, or not. It's got, a conditional assembly around it, so we can turn it off quite easily. This is what's left of the read routine now. I have a cache slot fill and a cache to RAM, copy cache to RAM routine that I've written here. And the reason I've done this is because I need to be able to fill the cache slot before writing into it if the BIOS wants to write to a sector that's not yet in our cache. I wanted to factor all that code out. The copy cache to RAM is really, what is that going to be used for? That'll only be called from this context here in the read routine. And that's for sure. But this one up here will be called from both the read and the write, and I didn't want all that replicated code. It was just getting too much. Way too much to deal with. Factor that sucker out, okay? When it's done, we have the usual error and return logic down here. So this is the whole read routine now. A little easier to understand, right? Put the track I want in the HL register and ask the cache logic, which I moved above, to fill that track into the appropriate cache slot. If there's a problem, go down to the error, squawk about it, go back up here and return with the appropriate error code. Put a 1 in the accumulator, clean up the stack, and restore the special stack code there, which is the same and mirrors the entry logic up here. Okay, so this is our new read routine. Now there's a lot of code that moved up the cache slot fill and the cache to RAM functions, but we'll look at that in a minute. And I also had to make it more generic, so there's a lot of tweaking and stuff in there. Those of you that have commented that I don't leave enough for other people to work on, this is your opportunity. I know this code doesn't work correctly because the write routine does not yet work. It still functions in the read logic functions in that it'll boot and you can type directory and you can run programs. It's probably okay, but this is a great time to look through this is the next week I'm going to have to go through here and basically debug this and convince myself that it's okay. The write routine I know does not work. So while I believe the cache slot fill logic works, because like I said above, the read routine is okay. What doesn't seem to be working, I suspect, is either the RAM to cache and the flushing of the slot. One of these doesn't work right. And, if you run this, be very careful. This most likely will corrupt your SD card. In fact, before I push this up to GitHub, what I'm going to do is I'll put the error return back in here so that somebody not following along that tries to run it without thinking about anything. I've been doing this for a year, and I've not yet pushed up stuff that I have found, anyway, is going to corrupt your SD card. But I'm pretty sure this will, all right? So when I push this up, here's what I'm going to do. Load A with 1, return. I'll put that in here right now. Guard against people who, I'll say, guard against those that do not read the doc, okay? I also, as you know, if you've been playing along, the main BIOS code that I push up to GitHub, until this works, still includes the no cache version that we know works correctly. So I won't even include this in the regular push. So if you want to, you'll have to change the include. We talked about that before. turn on the, the debugging from the console, and then you're going to have to remove this code in here as well if you actually want to work on this. But if you do want to work on it, you know that, you know what you're doing. You're going to be looking at the code in here, okay? So in the implementation here, the read and write routines both work the same way as they always have. We have to create our own local private stack. Talked about that before. Now, when I was going over the code that we've been using all year, I noticed a little problem here. Now, I probably talked about this many months ago, but, it wasn't in the doc, and I decided to remove this. Now, if we remember from the alteration guide, which I copied into the doc up here, what happens is when the BDOS calls the BIOS write routine, what it does is it puts a value in the C register to let us know whether we're writing to a sector for regular old, situation, like writing the data in a file, or if we're writing to a directory entry, or what we've got is this special case here, which I talked about before, which is an indication that we're writing to a newly used block, right? So what that means is that BDOS knows that this block that contains the sector that it's being written into here is the first time it has been used, or the first time it has been reused. In other words, it was not in use anywhere at the time that this write call was executed. All right. So we can take advantage of this knowledge by not going out to the SD card, reading in the whole block so that we can replace part of that block in order for the BDOS to simply write some data into one sector. And this, we'd have to do some more analysis on this, or go look in the code to figure out how nice, I should say, the BDOS really is when it's doing this. When they say first sector of a newly used block, is it the first sector of the whole 2K block? Remember, our disk parameter block describes our drive as having 2K logical blocks, or allocation blocks, as the CPM doc likes to call it, okay? Well, our SD card has half K blocks, and our CPM tracks have a half K in size as well. We talked about that. That has to match the SD card to make a lot of the logic here simpler, okay? So if this is the first sector of a newly used block, we have to ask ourselves, are we only going to be told this once and only once on the very first time a block is written into? And I suspect the answer is yes. And of course, the BDOS does this on a block basis. So my point is, this is going to be kind of hard to optimize as much as we could. So if you look at this down here, what I commented out is, this is really naive, all right? If they say it's the first sector of a newly allocated block, or one that had never been used before, then can we simply not read an entire track, which is what this logic is doing? Just skip the reading of the entire track. Well, yes, as long as the size of the track is less than or equal to the size of an allocation block. And yes, if the allocation blocks are aligned to the same boundaries as the tracks. So that turns out to be absolutely true in the case of the retro BIOS that we're working on here. However, if we play around with the disk parameter block, this may stop working. And that could be like the most annoying, incredibly subtle errors could creep in if we don't manage our cache properly. So right now, this is commented out. I'm going to leave it go, all right? Again, let's make it work and then make it better as we go. What I think the right thing to do here is to check to see if the tracks are aligned and stuff like that by looking in the disk parameter block, or at least do some simple hard code in here that we just simply reach around into the disk parameter block, hard code something to say this is okay or not okay based on the settings in the BIOS where we define the DPB for the drive that's being accessed here. I mean, this could be a huge problem. So I went ahead and put a XXX comment on there and just said, let's not do this for now. Besides, along with that, I didn't even bother to debug this padding routine. So we can look at all this stuff. I mean, like I said, there's great room for contributions here, those of you that want to play along. So what are we doing here in the write routine? I factored this thing way down as well. So here's me reusing the cache slot fill. We know that if we want to write something into a sector on a track, we need to first get that track into our cache. Okay? And if that fails, we fall down into the same error logic we had before. If it succeeds, we go down here to write data into the slot, and we have a copy RAM to cache, just like the cache to RAM we saw in the read routine above. And those copy routines, as we'll see in a minute, cannot fail because all they're doing is moving memory around in the machine. How is it supposed to fail, right? We have memory. We're not dealing with an I/O device that could tell us something bad happened, all right? So these we don't have to worry about, did it finish or not, is my point. When that is done, we have to flush the cache back out to the SD card, and we have to take a spelling course to learn how to spell the word flush. Hey, man, the S and the C are close enough for me to go with that one. Yeah, I know how to spell flush, for crying out loud. Moving on. If we cannot write the track back out to the disk, of course, we have an error, so we go back up to the same write error logic up here, that whether we can't read it or we can't write it. This message is no longer valid in both cases. I'm going to put a XXX comment on here. Is not always proper. I'll use that word, okay? Because obviously if the read fails, yes, the pre-read has failed. But if we come down here and the write fails, then the write flush has failed. Now, I think what happens also is that the cache slot flush routine also has an error message or something like that in there. So what I might need to do is not jump up to here, but just jump to here, or simply put some, whatever. I may want to rework this so that this is not so confusing to somebody who sees that message, is my point, right? So obviously, if you saw the write routine before, this is much shorter and simpler. Eventually, we fall down here, clean up the locally allocated stack. This operation does not affect the accumulator, so we then fall down to the return, and we return either the 0 in the accumulator or the 1 from up there, okay? So now this is just a matter of looking at these pieces of code that I've gone and factored out above, all right? So let's go back to the top of the file and get oriented here. So I scroll down. We've seen all the slot to tag and all the debugging routines up in there before. A slot to track, and then what do we got here? Slot to track, valid. That's the exit. That's a local label. We can set the tag. What else we got going on here? Track sector to address. Well, here's one of the things I had to factor out. We remember seeing this, and it was copied into both the read logic as well as the write logic. Vertically, there's a lot of code in here. Visually, I should say. These aren't a lot of bytes, but I wanted to get it out of the code and reuse the darn thing. So the way this works is I haven't really cleaned up the doc yet. Well, for now, I'm going to just say these clobber everything, even though they don't literally do everything. I mean, they don't modify the alternate register set and things like that. But for now, is a word of caution. This is all a work in progress. So I'll clean up the doc when we get done. How does this thing work? This is the part of the code that says, give me a sector number and a track number. What address in the RAM bank that has the associated slot is where that sector is located. So what do I do here? I got the track in the HL and the sector number in the BC. So I save the sector because it gets munged around with in here potentially. I don't actually recall, but it needs to ultimately end up in the HL register down here anyway. So let's go ahead and use the stack for that. Give me the slot, and then we get the slot address. And this is literally cut and pasted from the old code. When we're done with that, we need to put the slot address in the DE register, get HL back to having the sector number in it, multiply that by 128, add the base address of the slot, and we now have in the HL register the address of where the sector starts if someone has already set the RAM bank to map in the correct slot. Okay, a little debugging, and we return on our merry way. So I factored that out. What else do we got? Cache slot pad. This is commented out because I'm not 100% sure it works. Okay, I had enough trouble debugging the write routine, and I ran out of time this week. I'm sorry. We'll wrap this up hopefully next week. You know, work got a little out of hand this week. That's just didn't have enough time for the hobbies. Very upsetting. Anyway, what does this thing do? This thing is going to just simply pad with all hex E5s the entire slot that's defined by the track number in the HL register here. So what do we do here? We translate it to the bank number, turn the bank on so we can get to it. Then what we're going to do, we're going to calculate the slot address within the bank by using the routines we already talked about as well. And then we play our LDIR game to pad it all out with E5s. Then what are we going to do here? We are going to set the tag. Yes, we got to remember to do that too. This is effectively saying that we've read this in off the SD card. We're faking that, of course. And we got to remember to keep the tag up to date. Put the memory back to where it was and return. If you look closely, this routine does not use the special GPIO save area. And the reason it doesn't do that is because this doesn't call the SD routines and things where that is necessary. I just simply say save what it is, temporarily map in the bank I want, poke around, and then map it back to where we want it to be. What I probably should do if I think about this is move this up to here, because the set tag routine has to mess around with the bank that holds the tag, although it doesn't change the amount of code or the performance of the system, I guess. It doesn't really matter. I'll think about that later. Anyhow, that to me makes sense in general, but it hasn't been tested. I haven't been verified. It runs, but I haven't verified it. Here's the cache slot fill. So as the comment above says, this thing fills the cache slot by reading the track, right? This thing is the read operation that's going to call the SD driver. So in order to do that, this is not as efficient as it was when I just had it inline in the read routine, because it has to be more generalized, okay? Now, what do? I pass the track number in the HL register. The idea here being that, I mean, I could just go and load it out of the BIOS CPM track address variable that we have. But what I thought would be neat is to just have these slowly evolve these. Quickly would be better, but evolve these in a way that these functions can be parameterized, so I can use them for reading and writing sectors off the SD card and putting them into the cache and stuff like that, without worrying about whether or not the BDOS asked me to access a specific track and sector or not. We may see this more useful as we move along and improve the way our cache works and stuff like that. So, I mean, it's also generally good practice if it doesn't turn into a total nightmare, and in some ways it sort of is in some of the code in here. Again, comments below really would be appreciated. My Z80 programming skills are now, I'm at the limit, I guess. Having trouble, we talked about this before, deciding how I really want to pass parameters to these subroutines. I've looked at how some compilers work. So, like, for example, the SDCC compiler will allocate just save areas like, the BDOS does, where we have the CPM track, the CPM DMA address, and the CPM sector number, where you can just simply store all the arguments to some subroutine in those fixed addresses and then call the subroutine. Of course, the downside of that is that memory is used and consumed whether this subroutine is being used or not at all times. You can eventually run out of memory. Another way to do it is to push them all on the stack. Well, then you need a bigger stack, but at least you're not, wasting that memory to hold those parameters when the subroutine is not in use, right? And that's the technique I used to access the SD card when I'm in the reading and the writing routines. But as you saw, that code is not exactly the cleanest thing either. I need to kind of, pick a good technique and stick with it. So I'd love to have some discussion on that. Wander over to the Discord. There's some discussions starting to happen over there about other operating systems and firmware, monitors, and all these other things that people are playing around with Retro Board. So I know you exist out there. Please opine on this topic, because I just too many options. I'm seizing up. I can't even talk about it without getting stuck here. Too many options. I got to pick one. I'd love to hear some pros and cons and other insights. I mean, there are other options that people like to use. Anyway, moving along. So to fill a cache slot, we did basically, like I said, this has been factored out of the read routine. You've seen a lot of this before. I'm on this whole track number thing because what you see me doing is pushing and popping the track number over and over in here because I need to keep it somewhere, but I don't have enough registers to just keep it in a register the whole time while I'm calling all these other subroutines because they have clobber registers and stuff like that. So what I'm going to do is save the track number into the stack and then corrupt it while I'm calculating the track number that's actually currently in the slot that I need to use in order to do the fill. And this down here will say if it's already in there, I know I'm done. Okay, and we've seen this logic before, but what I've done is I put it in the cache slot fill algorithm here so that both the read and the write routines can both take advantage of this. I call this a Captain Picard style function. Make it so. All right, so this function will be called whether it needs to be filled or not. It very much simplifies the caller code. The caller has to make these decisions anyway. So what I'm going to do is I'm going to go in here and say, is the one I want currently in there? If it is, I'm going to just say, okay, fine, and return out of here. And as I look at this, it's not even clear that this works correctly. I told you there's bugs in here. I push HL. What do I do here? I'm calculating the value. Aha, I pop DE. The Jedi mind trick here. So DE is popped off the stack to match with this. So, okay, I was wondering, did I not clean up the stack before I did this here? I think I need more coffee. Anyway, so I save it. I calculate the track number that's in the slot. We saw that before. And then I say, give me the track number I want. Subtract what I want from what I've got. Talked about that before. And if we end up with 0, then we have what we want, right? So what are we doing in here? We say jump if it's not what we want down here. So this debugging code here is a little weird compared to what I normally put for debugging because this has real logic in here as well. And the reason I did this is so that when the debugging logic is gone, this thing falls down into the return if 0 flag is set. All right, so this is way better to write the code this way. So it just keeps falling through here if what we have is not what we want, okay? But what I wanted to do here is print a message if it's not what we want. So if we have a 0 after the subtract is completed, this will not happen, and we'll fall into here and we say we have a hit, okay? And we clean up our stack here. We got to clean up the flags is why I have to push AF here. It's not about the accumulator. It's about the flags so that we can say return if the Z flag is set right here. Okay, that means we already got what we want. Now, if we don't have what we want, then the Z flag will be off. We'll have a non-zero situation. Skip over this debug statement in here, and then it'll get down here to the return statement. The Z flag is not set, so it won't return. It'll fall down here, and it'll say we got a miss. Okay. Now we push DE back into the stack. In other words, put that track number back in the stack. This doesn't modify DE, nor does the subtraction here. It modifies HL, so DE still has the track number in it. Put it back on the stack because we need it to use it below, right? So this pushing and popping is the real big difference in this refactored code here. So keep an eye on what's happening with that. And I don't have a way to load HL with what's in DE directly, so I have to use two instructions here, which is fine. If they wanted to add that to the Z80 over the 8080, right? Remember, this is the Z80 here. If they wanted an extended instruction to do this, it would have to be 2 bytes long anyway. So they didn't bother with that because this is 2 bytes of code as well. Now, one might argue that the Z80 does not execute this as fast as it would a 2-byte single instruction due to the M1 cycle lasting longer than the M2s and so on. But in the greater sense of things, if you really think about it, this is only slightly slower than it would be if they decided to do a full-on special custom instruction for that. I certainly don't blame them for that. So we got to get HL loaded with the slot, or rather the track number, so we can redo the logic here to calculate the bank. We saw that before. Select the bank that has the slot in it that we want to put the data into, the same debugging we have before. And what are we doing here? Calculate the slot address within the selected bank. And then we're going to calculate the, So back to the pushing and the popping, right? So before you used to see a lot of load HL with the, the BDOS track number and so on. Now we just keep on peeking at the top of the stack over and over again to do our calculations in here. Then we do our command 17 to read it in, and we ask, did it work or not? If we got a zero back from the read routine, it's okay. So we end up down here. If we don't, we have an error. We got to restore the bank. Okay. And we have to invalidate the cache tag. Then what do we do here? We set the error to 1. Or something with 1. The other thing that's a little unusual about this is I don't necessarily return 0 or 1 in the accumulator to the caller. I return with the Z flag set if all went well. And I return with the Z flag not set if there's an error. So by ORing garbage in the accumulator with 1, okay, I guarantee the Z flag can't be set here. So that's the error state. If it's okay, we have debug, and then we say, what are we doing? We're going to set the tag to remember what's in the cache, clean up the bank select, and then I'm going to XOR A, which is the fastest way to set the 0 flag, which also sets A to 0, by the way, and we do a return. Now, why did I decide to change my, my course of action here and use the 0 flag as my, Boolean, the okay, not okay, versus just, loading the accumulator with 0 or not? Well, if you look at what happens when we call this routine, I don't want to have to then compare the accumulator to 0 or not. Okay? Half the time, if this thing returns, I've got like the OR instruction down there and stuff like that. It's easier for me to just use the Z flag in the conditional branch after I call this when this is used than it is to have to go back and then recompare the accumulator or not and stuff like that. Okay, so that's why I changed this style there. I think this works okay because it does work. Now, whether it's correct or not, I don't know. There could be some bugs lingering and some weird cases in there. For the most part, it runs, okay? So here's the other way around, the flushing back out. This one, I'm pretty sure does not work okay. So this is, you want to do a walkthrough on this if you want to run this, and I would not trust a good SD card with important data. Do not use this code. I've warned you enough. This may be broken. In fact, I'll put another comment in here. This is not like, this does not work. I know it doesn't. Now, it may be that this doesn't work because I forgot to load HL with the track number or something like that. It could be anything, but it definitely does not work on my SD card. I get a lot of debugging output, and it kind of like looks like it's supposed to be working, but it just does not work. Okay, so beware of that. We're going to say the same sort of thing. We're going to save the track number in the stack, and then we're going to pop and push to get it back as we go. Now, this thing is, you recall, is going to have to be backwards from the fill. So flush goes the other way. This is what we're going to call in the write routine after we know we have updated the slot in our cache, and we need to push it back out of the SD card. Again, we're using a write through cache in this design. So the write routine will always just end up calling this to flush it back out. So what is this thing going to do is we need to figure out what bank it's in, map that bank in. Then we need to go, what are we doing here? This is an old comment, so we want to write the slot contents to the SD card. Okay, I'll say the cache slot. We all know what that is, right? So we're going to grab the track number back out of our stack and do this same, this needs to be updated someday, right? We talked at great length about the fact that the beginning partition block number is hard-coded to hex 800. And then we're going to add that to the CPM track number, which is going to give us our physical block number, since they are one and the same once you add the base address on there. Since the block number is just simply shifted up from the CPM track number. Again, all went into thinking about how we wanted to define our disk parameter block for our SD card drive. And then we're going to do what? We're going to put a 0 in the DE register and push that, followed by the SD block number. We talked about this before. This is the same as it always was in the write routine, because we're preparing the stack to call the command 24, which wants a 32-bit value on the stack, all right? So we're going to do all that. Now, this is clearly wrong, because I just pushed the block number into the stack, and then this is probably why it doesn't work. and then I'm expecting to grab the CPM track number, okay? Now, if you think about it, this code here, this is just wrong. All right, do not use this. But I think it will still work. And here's why. This is actually real. This is your total red herring kind of a thing. So this is so wrong, okay? Why is it wrong? Because I'm expecting to pull back the CPM track number out of the stack, because I cut and pasted this out of the read logic. But up here, I'm pushing other stuff into the stack and burying underneath these values the track number that was in there before this started running, which is this obviously was designed to expect the track number to be on the top of the stack. That's not what's on the top of the stack right here, right? No. On the other hand, if you think about this, what are we doing? We're not pulling the track number out of there. We're pulling off the least significant 16 bits of the block number in this code. So that's wrong. However, if you look at what the track to slot does at the top of the routine, all it does is zero out the H and leaves L alone. Well, now if I can find out where we were, there's the fill there. I think that's it right there. This should be this is the flush. There we go. So because all that does is zero out the H register, that being this call here, okay? It turns out The L register here, I happen to know, has not been modified since up here. So, and the reason for that is because the partition base is set to hex 800. So this thing essentially adds 8 to the H register, leaving L alone. So when it does this, it is getting the wrong value out of the stack. Absolutely. However, this routine here zeroes out the H register, leaving the L alone, which still has, because this thing was never modified up here, and it was pushed out onto the stack up there. Technically, these two are not even needed at all to fall into this logic if we leave it the way it is, which is absolutely not a good idea. But these kind of optimizations are common in the old days because, as long as, this is true and as long as that's true, and in this particular case, it's okay, and blah, 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 this is the sort of thing that makes code so incredibly difficult to understand in every way, shape, or form. That it's just outrageous, okay? So it just so happens that removing these two lines right here will be the exact same thing as having them in there, all right? Simply because if you push it, pop it, and push it, you've accomplished nothing but wasting time. And because L never changed, technically this will work and get the right answer, but oh my God, I would never want to have to debug someone's code that wrote this. This is so bad, so bad. So no, this is not just intolerable. Don't do this. Do it the right way, even though you'll get the same answer. So once you've got the slot in the L register, the slot to address would also work correctly. Then we copy it into the DE register, and then we call this routine here to print some debug out. We could run it and see if it's doing the right thing, and I'm sure it is because of what I just explained up here, but that's just so bad. I can't tolerate that. We need to find a better way. And by the way, the better way would be, I think, to just reverse when this is all done. Since this doesn't modify the BC, I think that's what I did in the read routine above, because the same operation has to happen in the fill. I suspect if we reverse the order of these two, this will work. We can stick it in the BC. I'm going to do that right now. While we're here. So what we're going to do, we need to put that back in, of course. Get the track number into there, and then in here we'll put it in the BC register pair instead of the DE. Oops. And that way it'll survive getting through here. This needs to get the track number, add the base, and all that other fun stuff. Put that in the stack, which then buries our track number, and that's okay at this point in the code. We then come down here, and it says, here's the slot address that I want to be using, which makes sense. This debug is trying to print out the value that's in the HL register. This goes back to the older version as well. And then what has to happen down here is the DE register has to have the address in it that the command 24 is going to write from. So I have to say load D with B, load E with C. So now the comment here would be that BC equals the source slot buffer address, just so we can follow along with all this juggling all these balls in the air. So does this make sense? Point is, I can't put it in DE here because I'm clobbering it there. Of course, I could, this is stupid. Let's not do that at all. Let's put it in the DE register here. I'm not thinking. I need more coffee. Let's leave it in the DE register there. And instead of juggling all this, I can put this in the BC register. Okay? and then add it here, and then I can use the BC register for the, I mean, it doesn't matter what reg I use, I just need to have one so that I can add it to the HL pair, and this is legal, and I need to put a 0 into the stack, and it doesn't matter how I do that, just make it so. So the DE register will be left up here. Let's get the doc right. Actually, I know I did this last night when I was playing around with the read logic. Let's see how I did it up here. Yes, I did the exact same thing. This is the same logic up here. And one could argue, why isn't that factored out? Well, I mean, you can only go so far with these things. It might be that this should be factored out. Again, I look forward to your comments. What do we got here? We get the track. Then we have into DE. We get the track back. We add it to there. And then I use the BC just like I did before. Yeah, I knew I saw that before somewhere. I wrote that code last night. So, all right. So, okay, we leave it in DE. Then we put we played the game with the partition stuff. Put the 0 in there, followed by the partition value, the slot number. And then when we fall down here, DE will have the buffer address still in it, right? Doing a double check on the visual in here. DE doesn't get modified. And the 32-bit value is on the stack, so we then fall down here and clean up our registers. We just have to throw that away, and it doesn't matter what registers we use for that purpose. For some reason, I'm inclined to do this, just so that they match up here, although it's completely irrelevant. I could just say pop anything twice to get the junk out of the stack. So these don't modify the flags, so I can say, or don't modify the accumulator, I should say. And if A is set to 0 after the SD card routine, we're good. Otherwise, we're bad. This is the error message I mentioned before. And now we have to decide what to do here. What do I say? It's not really invalid if the write fails here. So, if the write does fail, what do you really want to do? So I decided it's not invalid because the write data is in the cache. We just can't flush it. So do I really want to do this here? I suspect the answer is no. Because this is the information that's in the cache tag is really describing what's in the cache. It's not what's describing what's on the SD. So, all right, I don't know. I haven't thought this all the way out yet. I'm pretty sure not doing this is the right thing. Looking forward to the comments. If the write has failed, we're going to return a 1 in the accumulator. Actually, this is old doc. We're not telling CPM has failed. We're saying simply that the read, that the write, boy, has failed. Too much copied code. All right. So when that fails, it falls down into the cleaning up of the bank and some debug, and then we restore the accumulator down here from when we saved it up here because we hack it all up in this logic there. Okay? And because we can get to the return routine in different ways, right? We can say, just warp in from up here, and we know that the whole accumulator had to be 0 if we come in that way. Otherwise, there's a failure, and we put a 1 in there. We need to retain the accumulator again as we clean up the banks and stuff and return out of here. So as dubious as this was, it's not likely that that would have caused any real problems unless I overlooked something. Let me know in the notes below in your comments. I'm still going to declare this as non-functioning because I don't expect that will help at all. or I even introduced errors. You got to relook at your code, people. Okay, so there's your flush and your fill. Now we have to copy things into and out of the cache from the memory. All right, so I have these copy cache to RAM and copy RAM to cache. So this cache to RAM is the copy of the old read code, but it has been left to be a little bit more generic than before. So the big takeaway here is we're going to see more times when we're playing around with the banks, turning the banks on and off, because these factored out pieces of code like RAM to cache, cache to RAM, fill, and flush need to play around with the banks, where before the read routine kind of only messed with the bank once on behalf of all these subroutines. So in order to make these more general purpose, our performance will go down a little bit, but because we have the cache, which speeds up the I/O so unbelievably huge, we can pay quite a performance hit in our code implementation simply because we're saving such an incredibly huge amount of time by not talking to the SD card if we don't have to. Okay? So, yes, I'm aware of how inefficient some of this is, but we're still better off. Win the war, not the battle. Okay, so this routine gets us really smack dab into what I was talking about earlier about how should I really send parameters to these subroutines and so on. And I just simply cut and pasted this code out and ran out of time, and I didn't think much about it. So I left the comments in here and say, hey, FYI, if you're going to copy from the cache to the RAM or the RAM to the cache, this is just going to reach out and use these variables from the major BIOS. Because right now, the only reason we even use them is to finish off a read or a write operation. So I'm going to use the BIOS read sector, track, and the DMA buffer addresses, those variables, those storage areas for the parameters of this code. And therefore, I didn't have to change, to pass it in registers and stuff like that. It just got really messy, and I don't know. If I'm going to do this by putting them on the stack and making these general purpose, which I think is a good idea, certainly a reasonable goal down the road, what I'll probably do is something similar to what I did in the SD card. While I push all of it onto the stack, and I put one of the index registers to point at the stack, and then use the offsets on that index register to access the various pieces of values in the stack, rather than going out and grabbing these values directly from the BIOS, allowing this to be reusable and not be welded into the rest of the BIOS logic. Okay, as a general rule, that's a reasonable thing to try to strive to achieve. I believe, making these functions more general purpose. On the other hand, I don't want the performance to go too much into the crapper, and I don't want the code complexity to escalate, infinitely as well, just to achieve a general goal that may not ever really be necessary. Okay, so again, I'm dying to hear some good comments. I know there's some great experts out there that have called me out on other things, either privately in email or on GitHub or whatever, even in the YouTube comments, the Discord and everything else. No one's perfect. I'm dying to hear a great idea on how to deal with this sort of thing. Again, I'm talking about what happens when you have to send parameters to a subroutine when you have too many for the registers that you have to work with on a CPU like the Z80. Anyway, what is this thing going to do? I want to go from the cache to the RAM. So this is my read operation, and we're going to have to figure out which bank it's in, turn the bank on, and this is just copying between cache and RAM. I may or may not need to do so much cleanup with saving the GPIO original value or the old one, or keeping this cached value up to date or not. Remember, we do this because we're going to call something like the SD card and the SPI drivers, which do daddle around with the GPIO value. So it has to know what it currently is. So it's critical that I update this if I'm going to call a subroutine that also uses this. All right. And I may actually do that because things like that doesn't do it. But if I ever call something to look at the tag table, it's obviously going to need to modify the bank and then put it back to where it used to be and things like that. So we have to be careful by haphazardly reusing this all over the place. And for all I know, maybe that's even part of the problem with my write logic below. I don't know. Anyway, moving on. This thing has to turn the bank on for the portion of the cache that has the sector in it that we want to transfer. We're going to grab what? The track and the sector number and call the new routine we looked at before and say what address is it supposed to be in the bank that it's stored within, right? And that we just mapped in up here, okay? Then we can go and do what? We load the track and sector. We call this. This leaves HL with the address of the sector in the cache. We then say, where's it supposed to go? And we then ask, is it in the high or the low bank? Okay. If it's in the high bank, then it's cool. We can go down here to the cache the RAM, and I put a D in there for direct. We can't have labels more than, I think, 16 characters with this particular assembler, so you have to be careful when these things start getting long. If it is not in the high RAM, we copy it into our bounce buffer first for 128 bytes using our LDIR. And then we go from there to where it's supposed to go ultimately. And that's where we have to turn the cache, or rather the bank, back to the original address so that it can get to where it's got to go from the bounce buffer to where the original BDOS DMA address is, okay? And again, I put some debug to let me know that I bounced it versus not. And then I just fall down into the wrap up and finish logic for the direct copy that would have gone without the bounce in the first place to finish it off for 128 bytes with our LDIR. This is redundant at this point because the if it was if it went by way of the bounce, okay, we talked about this before, this is redundant. If it did not bounce it, then this will be necessary, okay? We can reorder these operations maybe a little bit and kind of clean this up. Maybe that's a room for another improvement, but right now, this still matches what we did in the old read routine, and this still functions. I'm going to go with that word. It may not be perfect, but it functions properly, and the system runs. And we go back to the caller. Again, there's no error return in this case because this will always simply work. It's just copying data around. It will work as long as the code's not broken. Okay, and then this is going the other way. Take memory data from the memory in the RAM and copy it into the cache. And because the write operation doesn't currently work correctly, as I said, this might have a real bug in it. So what do we do here? Again, we're using the BIOS, BDOS variables directly in here. Again, it'd be nice to parameterize this, make it more general purpose. We need to ask if we need to use a bounce buffer to get it into the cache now. This is going to go the other way around. And what are we doing here? We're going to say is the we're comparing it to HL. So we want the DMA address. So we ask, is the DMA address big or not? If it's greater than 7F, the result will be positive, so it's all right. If it's not, we need to use the bounce buffer, and we're going from RAM into the cache. So what we need to do is first copy it into the bounce buffer instead of the second way, like we did in the read routine, the read logic. So that's going to be the destination. We print that out. The source address is in HL from up here. This doesn't modify HL, so we're good. This doesn't break HL, so we're good. That's good. This should not modify DE. Put that in there, copy it, and then we say the source address now is the bounce buffer, and we print that out incorrectly. certainly the debugging was wrong. And then what do? We save that in the stack because we're going to clobber it to calculate the bank that has our track in it, our slot. Like I said, this code doesn't work, so let's take a look-see here. So HL is the bounce buffer address. That's the source. And we save it, and we do all this fun stuff. We turn on the bank using the same kind of logic we did for the copying it the other way. Cache to RAM, that makes sense. And then we're going to say what? Give me the track and sector, calculate the address in the cache. So this is the sector address. That's then what? The destination where we want it to go, ultimately. We need to get that into the DE pair because this returns it in HL. Then we pop HL off the stack because it was saved way up here, which really just has the DMA address in it. I mean, given the way this is written, I could just simply load HL again with the DMA address, but this is kind of like, I want to make it parameterized at some point. We want to copy over 128 bytes. We do it. Restore the bank. And get out of here. Now, this is interesting. I think we found the bug. What happens if we don't have a bounce buffer? I mean, we can always bounce it. That's one thing. But what does this do? This is just nonsensical. What does it do down here? Oh, this is... Right, all right. So this is more clever than I thought. When we're doing the reading, because it goes the other way around, I'm used to thinking that way. I did a lot of work on that. Is this right? So I do this. If it's all good, if it's high, we go to the cache direct, copy RAM to cache direct. And if we do that, we know what is HL got the right value in it. Because like I said, this didn't work for me. It was terrible. So HL up here has the DMA address in it, which is the ultimate source of where we want to copy our data from. And then we come down here and we say, is that good or not? I mean, and good being, is it in the high bank? And if it is, we go to cache direct. We can pop that out, which is actually still okay right there, but it won't be okay when we fall down this way, all right? And then what do? We get this, and we calculate the bank. We put that in there. We calculate the address of the target for the DE register, and we pop HL again. I wonder if this has messed up the stack. I don't know. There's room for improvements here. I need to walk through this a lot more than just free associating about it right now. This could have some real problems in there. I need to sit down with another cup of coffee and draw this up. Anyway, that's the intention of this routine. And then what else? We've already seen the read logic, and I've already looked at this write logic down here as well. So both the read and write get factored down, nice and simple, cleaned up, long as we have this thing, factored out and keep the code down here nice and clean. This is easier to understand, in my opinion, even if the bug turns out to be right in here. But this code here should be the way to go. All right. This style, this structure, right? The simplification of these routines. This is very desirable, especially because what I want to do is evolve this to having more sophisticated and fancy versions of the cache logic, like associative caches and things like that. So with an associative cache, what would happen is we would simply change replace the mapping functions. Okay, this read and write logic here, in other words, shouldn't change at all. these routines should work whether we have a direct map cache or a associative cache and stuff like that. So will the copy in and the copy outs and stuff like that. What will change is the functions way up at the top that have to do with deciding where the slots are and what banks they go in. These up here should be the only things that change if I do it right, especially like this one. If we do this right, then these are the only things we'll have to change when we want to improve the way the cache works by using different types, all right? So very much a work in progress this week. Sorry I wasn't able to get it debugged and say, hey, here's our first release, which I like to try and normally do. On the other hand, this is a gift with icing on the top. Anybody that wants to help debug, this is the time to jump in there. I hopefully left it in a state where it'll even, or at least compile. That's great. So when I push this one out, if we look at the status here, I will not update this file. You're going to have to hack it yourself to turn on the direct map cache logic, because this is the state of mine is right now. I have the debug on, but the one that's in GitHub is off, and the one in GitHub uses the no cache, and mine that you're looking at here, when I'm tinkering around, if you want to play with it, you need to turn the direct map cache on, all right? So what I'm going to do is push up this broken code today, only this file, all right? So please have a look at it. Let me know what you think. Again, I'm really looking for ideas on what's the best way, what's a good way, a nice, sane, reasonable, efficient way to pass parameters to subroutines without creating a big mess. And maybe somebody can tell me what's wrong with my write routine. Anyway, thanks for watching. If you want to support the channel, go ahead and help me debug the code, or maybe become a Patreon. Send some comments below, thumbs up, share links to the videos. Anything like that's going to help the channel. Thanks for watching. We'll see you on the internet.